Okay, hello everyone. Welcome back to the AutoML seminar. This is actually going to be the last session before the summer break. And yeah, it's a very great pleasure to introduce our two speakers today, Elena Raponi and Nikki von Stein. They are both researchers at the University of Leiden, and they're going to talk about today a little bit how we can utilize large language models to automatically generate optimization algorithms. And with that, thanks a lot for joining today, and please take it from here.
Great.
Thank you.
Thank you, Aaron. Um, yeah, it's an honor. It's a pleasure to actually conclude this amazing season of the AutoML seminar. I hope it's gonna be a great conclusion of it. As Aaron said, we are gonna talk about LLaMEA-BO, which is a framework which is based on evolutionary computation and usage of large language model to evolve code bases, and in particular, its application and extension to Bayesian optimization algorithms. So a little bit an overview of today's talk. It's going to be composed by two parts. One focusing introducing LLaMEA, and the second half talking a little bit more into detail about LLaMEA for Bayesian optimization. So two parts, two speakers, and a couple of slides at the beginning to give you a motivation for this work and some background information. So we are working in the context of black box optimization. You see the black box on the right. I think that all of you are familiar with it. We are dealing with a problem for which we don't have any analytical formulation. And essentially, we know nothing except for the values of points that we might query. So if we input x, we will have as an output f of x, but we don't have any insight on about the inner mechanism of this black box. And when does this happen? Many times in real life. For example, if you are dealing with simulation models, you know what is the input parametric configuration, you run your numerical simulation and you get an output. You don't know anything about what's happening in the box. Real life experiments is the same in chemistry, biology, crash tests, and so on. Or, for example, for legacy code, when you have no access of what is inside a library. These are just some applications in structural mechanics, which is in particular the field I'm working in. You have crashworthiness, you have fluid dynamics applications, topology, material distributions applications, and in general, we always want to minimize or maximize an objective function subjected to some constraints, but we don't know anything about the analytical forms. So these are examples, and in particular, these are good examples for Bayesian optimization because in general, you don't have a very big budget of evaluations that you might use for your optimization procedure. And this actually brings me to the next slide, which is what does cost mean, right? And it is a metric for us to understand how many resources we have to converge towards some near optimal solution. And we can deal with cheap problems, cheap functions to evaluate. And in that case, we have thousands of evaluations which are available, or we can deal with highly expensive problems where one simulation has a very high cost. And typically we have budgets which are lie around 200 evaluations. And for LLaMEA-BO, we will actually work in the second context. In general, though, there is a huge class called metahoristics of algorithms, which are based on query-based schemes, essentially. So, and these are computational procedures that determines the most convenient solution given a certain metric which represents quality. I think that we are all familiar with this. But then some question raises, which is what is the best algorithm for our problem? And in the evolutionary computation community, essentially this is like quite a big deal because a lot of algorithms have been introduced in the last decade with teeny tiny differences between each other, but all of them are grouped by the same underlying thinking, which is biological evolution. So based on what Dennett says here, evolutionary computation is based on the principle behind natural selection, which is a universal algorithmic process, a mindless mechanism, he says, that can generate complexity, intelligence, and even consciousness without the need for a designer or central planning. So essentially, when we design an algorithm, we can use underlying mechanisms like natural selection without having like a master controlling from the top what's going on and just basing it on natural evolution, selection, mutation, and recombination mechanisms. So evolutionary computation and evolution strategies is what is behind LaMEA. And essentially, we evolve prompts to give to LLMs to generate code bases through an evolutionary computation schemes. And in general, how does this look like? We have an initial population, we evaluate our samples, and then we have selection mechanisms to understand which samples are the best from a certain population. We recombine and mutate these best individuals in order to generate a new generation of solutions that are evaluated. And then again, this loop is repeated until we have a population of individuals which are always better and better, become better and better, based on some metric. And in order to understand how good a certain evolution strategy is, we can do a lot of benchmarking. And one tool that we can use to do it is a IOH profiler, which is also a very strong component of LaMEA because, as Nikki will say, we evaluate during the generation of baselines of code bases. IOH profiler has a part which is the experimenter part, which is built on top of Coco and Bebob and essentially allows for easy integration of benchmark problems, translations, parameter tracking, and so on. And then a post-processing tool, which allows to make nice plots like the one on the right and understand the performance of algorithms, anytime performance, and also end of budget. And just one last thing, why do we care or mention Bebob here? It's a benchmarking suite, which has a quite varied set of benchmarks of analytical functions, which have completely different landscape characteristics, going from unimodal functions like the sphere function at the top to extremely multimodal and irregular landscapes like the Gallagher function at the bottom. And with this, I hope it was enough as an introduction. I would hand it over to Nikki, who will walk you through automated algorithm discovery.
Yes, thank you very much. So automated algorithm discovery and also what also led to LaMEA in the end started roughly with the work of FunSearch by Google DeepMind, where they basically showed that with an evolutionary process and a lot of technical details like an island structure and several populations, they were able to generate new solutions to different problems and derive new heuristics. Well, FunSearch was built to work on a particular small placeholder part in your code, and then it would use some quite cheap pre-trained large language model to perform a lot of these evaluations and generations of heuristics. And it would then keep these programs in a database that it will draw from, and this would continue and continue. It had several downsides. For example, their experiments in their paper took roughly 4.5 million evaluations to find these new heuristics. But all in all, it seemed a very promising approach. Then roughly at the same time that we designed LaMEA, there was also the work by the group from Hong Kong, which is called Evolution of Heuristics. And Evolution of Heuristics was heavily also inspired by FunSearch, where they not only evolved these heuristical code snippets, but also a natural language summary of the code, which they showed could improve a lot the efficiency of this procedure. And they mainly focused on combinatorial optimization problems such as online bin packing and traveling salespersons. But they still focus on very limited number of lines of code, like roughly in the order of 10, that they then insert into a larger code base where it would be used as a heuristic. Then there are some follow-up works based on that, like Re-Evo, which includes things like reflection or reasoning inside the LLMs. And again, this would be used then mainly in combinatorial optimization literature for generating these small improving heuristics. And a few months ago, Google came with the next version of their fun search called Alpha Evolve. And Alpha Evolve is actually very similar as LaMEA, as we will also see later on. And it can evolve larger code bases. It uses therefore also some tricks in that it applies a diff. So the difference of the code is being generated instead of the complete code base. It uses, of course, the Google Gemini LLMs, and it's really for general purpose algorithms, but can also be geometries or logical problems, etc. Unfortunately, this is not open source and therefore also not really reproducible, but they showed some great results. Then particular as background for the LLaMEA-BO is what came closest to it was something called LLaMEA-BO, which is basically a Bayesian optimization algorithm where each component, like the warm starting, a sampling, and a surrogate model, is being replaced by something that the LLM is providing. It requires therefore also 3 large language model calls per function evaluation, so it's rather expensive, especially if you don't have the hardware to host your own large language model. And it does show some very good results already from the start of the search, which might also indicate that it has some knowledge of the problems that it's being used on, but we will come to that later. Also good to know is that in terms of benchmarking for this large language model aided evolution of code, there is now also some work going on from us where we really want this benchmarking to be done well, because we see there are many pitfalls in the literature where only single runs are, for example, presented, or where only the final results of the generated code are being evaluated against baselines. So for that, we also introduced this benchmarking suite where we draw on our knowledge from the black box optimization benchmarking that we already had. Then I've been speaking about LaMEA already a little bit, but I have not really introduced it yet. So let's go ahead and show you. So the initial idea that we introduced in 2024 was really to try to keep it as simple as possible. Meaning we apply here a 1+1 evolution strategy, meaning we have one parent at any moment in time, and we only create one offspring, so one individual inside the loop every time. So we start with some problem specification. This is still the part that you need to provide as a user. So you provide what is it that you're trying to solve. And this comes also with a code snippet that should be as well, we started it as small as possible. For example, in the original work, this was just a code snippet of a random search. And then we asked the LLM, give us a black box optimization algorithm that performs well on a large variety of landscapes. That's like the problem specification. Then we send that to an LLM. In the beginning, we use GPT-4 a lot. This generates some algorithm. We load the algorithm. We see if it contains any errors or not by just applying it on a small test instance. And if it succeeds, then we do some rigorous benchmarking using the IOH tools to get a good anytime performance overview of the generated code. This information, together with any error feedback, if it was there, we combine and we keep in our session history. We then select, so we take the best so far algorithm that we have seen, and we simply ask the LLM to refine or to redesign the algorithm in order to improve it. So that's our mutation. And we varied this mutation in a couple of ways to see what works and what does not work. This continues until our evaluation budget is exhausted, and then we have our best algorithm so far. So in pseudocode, that would look like this, and basically, so the big loop here is what really matters. And we, in the beginning, experimented mostly with evaluation budgets of 100, meaning we generate 100 algorithms that we do a complete evaluation on, in this case, on a test suite called BBOB, where we test the generated algorithms on. The specific prompts that we used are given here, but basically you have some detailed task prompt where we say that the specific structure of the code, so it should have an initialization function, and it should have this call function that receives the function to be optimized, and some formatting code so that we know how to parse the generated code bases in order to execute them. And we have some feedback prompt, which is basically the mutation operator, where we tell what the scores were of the generated algorithm so far, so that it has some global context. And then we select, we give the full code of the selected algorithm that we would like to refine. So how does it actually work? So on BBOB, so the black box optimization benchmark suite, we consist of 24 functions. Elena already showed you some images of 2 of these functions. So there are 24 different ones. They also have different instances, meaning rotation and translation. And so we used here 3 different instances per function and 3 different runs for the stochasticity. And we use an evaluation budget of 2000 times D, so in this case 10,000 function evaluations in 5 dimensions. And each of those generated algorithms, so in this case 100 generated algorithms, was evaluated on that complete set of 24 times 3 times 3 evaluations. And the performance measure that we use here is an anytime performance measure, meaning we don't only care about the best point it found, but we care about the convergence speed. So we measure basically the area above the convergence curve, given that we know the optimum of the function. So how did that go? Well, we tried several mechanisms and several LLMs in the beginning, and we figured out that the GPT-4 Turbo in this case worked best, and it got in the end some average AOCC scores of about 0.55. Now, we still don't know, of course, how good that is, but I will show you later. Also, in comparison, we modified the evolution of heuristics. That was actually not really developed for this kind of problems, but after some modifications we could make it work. And we showed that in this case our approach was beating it. And we also run it with just random search to see how much evolution really mattered. So if we just query the LLM 100 times to generate an algorithm from scratch, basically, how could that work? And here we really see a clear gap where evolutionary computation just shows its worth. These LLMs generated the algorithms, but that also means that they generated the names of these algorithms. So we tried to dig a bit deeper in what kind of algorithms are actually generated. So here you see a word cloud with all the words that appeared in those algorithm names. And so some are clearly just stuff that it added to show that it tried to become better, like enhanced and adaptive and dynamic and whatever. There are also some fancy words like quantum and harmony and some other ones that we would maybe not want to have these algorithms inside because they don't mean that much. But overall, they were quite meaningful, as in they usually also said what the algorithm really did. For example, this surrogate-assisted differential evolution combined with covariance matrix adaptation evolution strategies actually did what the name suggested. We looked at how much these LLMs then mutate the different code samples. So in this figure, we see the pairwise difference ratio of the parent versus the offspring. And here we see that, especially if we look at GPT-4, the mutation is quite large, right? So around 40%. And with GPT-4o, for example, that's a lot lower, like around 20%. Also, in the naming of these algorithms, we see this phenomenon. So these results are quite similar. But how does it then really work against human-designed algorithms? So we tested a few of the best generated algorithms extensively on different instances than what we used during the training. And here we see a comparison of these of the best ones against some very good human baselines. So we have a standard CMAES, which is already quite often winning bebop contests. We have a differential evolution algorithm, and we also have a very fine-tuned CMA algorithm from modeler CMA package that was with a budget of 50,000 different configurations. We optimized that specifically on this on 5D instances of bebop. And there we see that this funnily named algorithm, ERAT's Quantum Flux Ultra Refined, actually won from that highly tuned CMAES. And we also see some of these other algorithms that perform quite well in the beginning of the search, so up to around 1,000 function evaluations, it still beats this highly tuned CMAES. With this best generated algorithm, we also won the Anytime Algorithms for Many Affine BBOB Functions Gecko Award last year. And this year, we also won the same competition with also again a LLaMEA-generated algorithm, but we were able to even improve the results of last year. So how does the LLM actually do these mutations? Well, we looked into the differences between the code snippets, basically between the parents and the offspring. So sometimes a mutation is just tuning hyperparameters. So the LLM is just trying to change, for example, the rate of crossover or the mutation rate or whatever, or the population size. It often also just updates some comments in the code to basically explain what it's trying to do. And sometimes these comments make sense and sometimes not. And quite often it also introduces some new strategies. Well, when we saw that, we thought, okay, this hyperparameter optimization, that's actually a bit of a waste to ask a large language model to do some hyperparameter optimization on an algorithm. So we came up with an extension of LaMEA, which is LaMEA-BO, where we basically use hyperparameter optimization inside the LaMEA loop, in this case using SMAC, but we could also use other hyperparameter optimizers, where we ask now the LLM not only to synthesize a new algorithm, but also generate the configuration space in a dictionary format to basically optimize the generated algorithm. Because we use many instances inside the evaluation of these algorithms, we can also use an instance-based hyperparameter optimizer, and in that way, we improve the code already from the very beginning a lot. So just to compare with vanilla LaMEA, we see that we already start very well, and we can still improve and find better algorithms. So this is on the same experimental setup for Bebop, but we also showed that this generalizes to other problem domains like combinatorial optimization. So for online bin packing and traveling salesperson problems in this case, so that we could better compare with EOH, for example. So here we have the results on online bin packing, where LaMEA, vanilla LaMEA could not, well, it was winning at some point, but in the beginning it's not that good. And LaMEA-BO starts already very good. Especially for traveling salesperson, this result looked, I would say too good to be true almost. And we also did some inspections, and basically we figured out that the problem instances that also EOH introduced in their paper for this traveling salesman problem were actually just too simple. But LaMEA-BO basically found within 10 evaluations the optimum of all these problems. So we then also extended this evaluation to more realistic TSP problems to compare the best generated heuristics that were generated on these simpler instances. And then we've basically figured out that many of these generated heuristics from EOH and also LaMEA-BO are not that significantly different on these real-world problems. We could generate these in less than 20 LLM calls. So as a partial conclusion is that in this case, LaMEA-BO generates algorithm on par with EOH, but in a much shorter fraction of the LLM prompt budget, and therefore also a fraction of the cost. Then I will switch back to my colleague here about Bayesian optimization.
Thank you. Okay, so I hope there are many enthusiasts of Bayesian optimization here online. Yeah, here I'm gonna discuss what we actually managed to observe by modifying LaMEA in such a way that it effectively addresses BO generation tasks. So I like to start with a sentence about Bayesian optimization in Roman's book, which says that Bayesian optimization does not refer to only one particular algorithm, but rather to a philosophical approach to optimization grounded in Bayesian inference, from which then an extensive family of algorithms has been derived. So like in the engineering community, it was originally known as efficient global optimization, which was essentially just one BO algorithm, what we today more or less call vanilla BO. But starting from there, a huge class of algorithm based on Bayesian inference and surrogate modeling have developed. So I think, that we kind of know that we start from the assumption that we don't know the objective function that we want to optimize. So the first steps that Bayesian optimization does is placing a prior constant, usually distribution, and then it refines it. So the idea is that BO models the underlying function with a probabilistic surrogate. And with no data, the surrogate just predicts constant behavior. But then when we observe new data, we can actually fit a model to the data, which is the blue line here. The blue line plus areas, because the blue line is the mean approximation, while the light blue area identifies the confidence of the approximation made by the model, right? So the uncertainty in the model of that function. So you can see here that this uncertainty grows as we move far away from the black observations, because of course the model is a little bit more unsure on how to predict the underlying function far away from the observations. Based on mean and variance of the model, we can actually define what is called an acquisition function, which is a helper function that we maximize in order to understand what point is convenient to query next. For example, here is this circle over here, and it means that in the following iteration, we were gonna add to our sample set a new point. So we observe our function by querying a new point, and this point becomes part of the data set. So our posterior distribution adapts both mean and uncertainty in the model to the new increased data set. Okay, I could write formulas here, but I think that they're not really needed. What is more needed in this context of this talk is to emphasize the modularity of the Bayesian optimization pipeline, right? So I mentioned an initial sample, and then based on this, we actually fit our surrogate model. So this is the second component. And based on the mean and variance in the model, we can actually define an acquisition function that we maximize, and we address like as an inner black box optimization task, essentially. So we also need to select an optimizer or an optimization technique procedure for optimizing this acquisition function. Of course, after the initial sample happens and after a new sample has been suggested by optimizing the acquisition function, or a batch of samples have been suggested for evaluation, we perform evaluation and we update the sample set. Yeah, essentially this is iterates. So we repeat steps 2, 3, 4 in loop until some termination condition has been met. So this is what we need here, and this is what makes Bayesian optimization a perfect candidate for automatic algorithm configuration, because it is modular by nature. So yeah, it seemed kind of obvious to us to try to extend LLaMEA. This is the similar to the framework that Nikki presented before. The only difference is in the template that we provide the LLM with, which is a little bit more structured. Meaning that we require the generated algorithms to have this 4-block structure, even if they can be like kind of modified a little bit, but still we want that general structure. Then we work with the bigger population sizes in the evolutionary evolution strategies. So we don't have a 1+1 only, but we have bigger population sizes, which allows for more exploration. And we need to define opportune crossover operator in such a way that these these bigger exploration capabilities could be actually be exploited. And yeah, this is definitely. Also, we ask for some diversity in the original population, and that can also be seen from this diversity initialization prompt. So essentially, we ask the LLM to behave as a very skilled computer scientist, similar as in LaMEA, and to start from a diverse, like a set of code bases following the BO template that you can see again on the left here, which is as diverse as possible as original parent population, from which all the steps of standard evolution strategies happen. Okay, so selection, mutation, recombination, and evaluation and selection again, and so on. So we have our mutation prompt being a certain code base. We ask to mutate it in order to improve it based on always the same metric as in LaMEA, anytime performance, and a crossover prompt, right? So based on two code bases that in the population, we actually ask the LLM to combine, which is quite easy given the, as I said, the modularity of the code bases that have been generated, which follow the classical BO pipeline. So these are the main novelties compared to LaMEA, and this is how it worked. So essentially here we tried many configurations, many different configurations of the evolution strategy, but essentially what we noticed is that by increasing the population size, and especially with comma strategy. What does it mean, comma strategy? Is essentially least elitist approach, meaning that we select the new population of code bases only from the offspring population of the previous iteration. While if we have a plus strategy, we actually put together parents and offspring, so it can actually be a little bit more conservative because we keep information like during the various iterations. Okay, yeah. So here the orange line at the top is a 416, 16 strategy, and it is the one that performs better. In this case as well, we generated the code bases by evaluating them on 5D. So dimension 5, and only on a few representative functions of the BBOB benchmarking suite and specific instances. Then once we essentially found we found the best performing code base based on this internal evaluation, as you will see later, we actually evaluated the winners on much broader benchmarks. So maybe what's actually useful to check here is that during the evolution of the code base with the help of LLM prompting, we go from very simple strategies characterizing the BO pipeline, so simple and very well-known acquisition functions like expected improvement, upper confidence bound, and very simple sampling schemes like Sobol sampling, Latin hypercube sampling, and so on. And we actually get with the evaluation, within the evaluation budget going on, we get always more sophisticated BO algorithms. At some point, they look for more explorative capabilities by using k-means sampling or partitions, for example. And only at the end, we actually end up having trust regions, which we know being a very well-performing technique in Bayesian optimization, especially for high-dimensional. Very simple, but very practical and well-performing for high-dimensional Bayesian optimization. So the code actually evolves. It's not starting from one algorithm and refining it. It really changes during the evolution. ATRBO was one of the best algorithms that we found. It is based on trust regions, indeed. And it is very similar to, not very similar, but like the big part of it is similar to a vanilla BO, but it actually defines trust regions to sample points on a hypersphere where points are sampled uniformly in volume. And also, it has an update rule on the radius of this hypersphere and also on the hyperparameter that defines the exploitation trade-off during the optimization of the acquisition function. So there is a lot of parameter control and updates based on performance. Here you can see like a comparison of the performance of the generated baselines in orange generated code bases in orange compared to established baselines like CMAS, HIBO for Bayesian optimization, Turbo 1, and LLaMEA-BO. And you can see that when validating our method on the whole BBOB suite and on different instances than the ones that were used for generating the code, you can see that also going to higher dimensions. So we generated the code base at dimension 5, but it extends also to 10, 20, and 40. So we get performance which is competitive or better than established baselines. Here is just a table for statistical significance, but essentially it says the same thing. ATRBO and Trivol were the generated code bases that performed best and better on the right than all the established baselines that we took into account. Here, if you want to have an overview on the 24 functions of the performance, you can see that dashed lines are the baselines, plain solid lines are the code bases that we generated. The lower, the better, because we want to minimize loss or regret. And you can see that the lower envelope of these curves is almost always some solid line. So we were quite happy to see the anytime performance also based on convergence. Maybe some attention here. You can see that on F23 and F24 there is ATRBO is predominant. And then we wondered why, right? Because this is such a big dominance. Essentially the reason is that the functions are highly multimodal. For example, F23, this is like the Katsura function. And you can see here that it's composed by many, many peaks. And the localization scheme techniques used by ATRBO allows for exploiting very well one identified peak during the search of the optimizer. So you can see this is like the loss. And here you have two different versions of ATRBO. Rho is essentially the scalar that we use to rescale the radius. Essentially, you can see that as soon as this radius goes to 0, to very low value, we have this huge increase in performance here for the blue and here at about 120 for the orange, which means that we are exploiting very, very well the local area, and so one of these peaks. We also checked how the generated baselines performed on ML tasks, in particular on a basemark, where each task is a pair of dataset and model. We decided to actually work on basemark because we wanted to compare to our kind of main competitor, which was LLaMEA-BO, even if the inner functioning is completely it's completely different, but still they both use the LLMs for BO. And we can see that we can actually be competitive even if the methods were generated for completely different tasks. Here we have dimension 15. For the synthetic benchmarks and lower than 10 for the established benchmarks. We can see that, yeah, we can perform well, except for the 3-based strategies where LLaMEA-BO is still dominating. But we were quite satisfied to see how well the generated code bases worked on completely different tasks. Maybe here just some remark on the super good performance of LLaMEA-BO on for super vector machines on synthetic benchmarks, which we cannot really explain, but it was very interesting to see. Last, I think that it's worth mentioning that LLaMEA-BO takes much more, which was this competitor, because it prompts during the run the LLM many times, while we actually have a CPU time which is lower than the one of Turbo 1, which is this trust region-based Bayesian optimization algorithm, which is super well known thanks to the Thomson sampling to perform quite fast. So we were very satisfied with that. And I think that it's time to conclude. So yeah, we saw that LaMEA can effectively find strong algorithms, which are on pair and sometimes even surpass state-of-the-art algorithms. Is the first method, LLaMEA-BO, instead, to produce complete BO, Bayesian optimization code bases. And what we generated can actually generalize quite well. And we can actually see hence LaMEA as a framework for algorithm construction, which is not only limited to one task, to one optimization task, but can actually generalize across different tasks. And depends, of course, on the LLM and the prompts that we use, and it can work for different types of search spaces. The computation, I'm almost done. The computation cost is still relatively high. And of course, the mutation rate control, some mutation rate control or some more sophisticated operators could actually be introduced based on the task that one addresses. And yeah, last benchmarking of LLM-driven is discovery. Algorithm discovery is still at early stages, so there is a lot of work to do. If you're interested here, you have our QR code. I would like to mention that this is the result of joint efforts of the natural computing cluster that we work in, and we're happy to represent all of them today. And yeah, with this, we would like to thank you all for listening to the talk, and of course, we are very open to any type of questions that might come. Thank you.